Today we're going to finish up the Chapter 8 notes, and we're finishing up the periodic trends. So we've already done trends of radius, so I just want to review a quick second if this computer will cooperate. One of them was the radius increases left and down on our periodic table. This is one of the big trends. So if you saw on a periodic table and you want to compare sizes, so if you want to see which one is the biggest, which is smallest, the element that is first left and down is the biggest, the one that's first up and to the right is the smallest. These are, again, general trends. This does not mean that every single one that's that there are no exceptions to this rule. So we're just talking about general trends. Okay, then we talk about atomic radius. So where is also this useful? Chemistry in action. Could there be a third liquid element on a periodic table? On our periodic table, there are two elements that are liquids on many periodic tables that are colored, at least. Like you see different colorings. If we're in a classroom, you see the periodic table in the classroom wall. Bromine and mercury are blue colored on the wall, which signifies that they are liquids at room temperature. So there are two liquid elements at room temperature, bromine and mercury. If you have pure bromine, you have pure mercury. They are liquids at room temperature, 25 degrees Celsius. There could actually be another element that is a liquid at room temperature, and that is francium. Now we'll get to why in the world we don't exactly know why it's a liquid or not. Okay, if we took the alkali metals, lithium, sodium, potassium, rubidium, cesium. So if you look on the periodic table, group 1 elements, it goes straight down the list. Lithium, sodium, potassium, rubidium, cesium. After cesium is francium. When you plotted the melting temperature versus the atomic numbers, you would see a nice curve. Okay, this is obviously not linear. It's more like exponential-ish. So you'll see a nice curve to this thing. And lithium having a melting point about 180 Celsius, sodium was about like 100-ish Celsius, potassium, rubidium, cesium. Well, francium is way over here. Francium, I don't remember the atomic number of francium without looking at the periodic table, 80-something. Oh, well, it's down here. Whatever, 80-something. It would, if you extrapolated the line, it probably is about under 25 degrees Celsius. Meaning francium's, if you had pure francium, it probably is a liquid at room temperature, 25 degrees Celsius. Now, why in the world do we not know and almost don't care if francium's a liquid at room temperature? Because francium is an extremely, extremely unstable element. When it's created, yes, it's created somewhat in a lab, because when it's created, it has a half-life, meaning it's only stable for about 21 minutes. And then it transforms into another element. It goes through a type of nuclear reaction. And it breaks apart. Francium atoms just break apart into more simple elements. And it only lasts for 21 minutes. And we're talking about like a few atoms, of 1-2 atoms at a time. And because of that, since we can't like exactly purify it and it's so reactive, you're also not getting pure francium. It's francium, I don't know, it's oxide, it's francium some other compound. It's not pure francium. So this element is extremely reactive, extremely unstable. We don't have pure francium. So that's why we don't exactly know, and it doesn't really matter because you'll never have pure francium anyways, but it probably could be a liquid element. Okay, if you could somehow purify it, and well, you can't control it from breaking apart naturally. Okay, but if you had a whole bunch of pure francium, which is highly reactive and also quite radioactive, so you probably don't want it anyways. But if you did, it probably would be a liquid at room temperature. So there could be a third liquid element, francium, on a periodic table. But at the same time, it doesn't really matter. Okay. So, next thing. There's two more trends I want to get to, and that's the last bit of these notes. Next one is called ionization energy. Let me define it first. Ionization energy is the minimum energy in kilojoules per mole required to remove an electron from a gaseous atom in a ground state. So if you can somehow magically, this is hypothetical, if there's an atom and you could just grab there, take your hand, and not that you could of an atom, but you can somehow grab and rip off an electron. That's a general idea, okay? How much energy does it take to remove an electron from an atom in its gaseous form, okay, in its normal, what's called ground state, okay? So if you have a normal atom and you could just somehow pluck off, it's not that simple, but you know, how much energy does it need to pluck off an electron? That's the definition of ionization energy. So ionization energy, remove electron becomes positive if you remove electron. It's called the first ionization energy. Remove 2 electrons, or second one, it's called the second ionization energy. Okay, you want to remove a third electron, it's called the third ionization energy. Just so you know, the first ionization energy is always less than the second, which is always less than the third. And the reason for that, why second ionization energy is always greater than the second, first, and the third is always greater than the second. When you remove an electron, the atom pulls in the fewer electrons more, and so it's harder to remove the second one. You remove a second one, it pulls in a fewer electrons even more, because the number of protons don't change. Pulls in a few electrons more, and it's harder to remove a third electron. So that's why second ionization always more than first, third is always more than second. Okay, so second is always greater than first, third is always greater than second. There is a fourth, fifth, sixth ionization energy, and so forth. There is a table for all this. These are not numbers you would ever memorize. Here they are. And, where's my face? So hydrogen's first ionization, second, third, fourth, Notice for any element, second ionization energy is always greater than first, third is always greater than second, fourth is always greater than fifth, fourth is always greater than third, fifth is always greater than fourth, and so forth. Why is there no second ionization energy hydrogen or third ionization energy helium? Well, quick, easy answer. Helium is element number 2. There's 2 protons, 2 electrons. There's only 2 electrons. You can't remove a third electron if there's only 2. So that's why there's no numbers right there. Okay, look on here. Just for the first ionization energy. Ignore the second, third, fourth, fifth, sixth right now. Just look at the first ionization energy. Do you see a pattern between Z, atomic number, and the first ionization energy? Do you see a pattern there? Probably do not, is what my guess is. Looking for a pattern between Z, atomic number, and the first ionization energy. Well, what have you graphed it? Let's graph, this is the x-axis, this is a y-axis, just like you do in math. X-axis, atomic number, y-axis, first ionization energy. X-axis, y-axis. Well, magic of computers is done now. Okay, atomic number versus first ionization energy. What do you see as the top here? Like helium, neon, argon, krypton, xenon. What type of elements are those at the top peaks here? If you look on the periodic table, ignore the shell part right now. Helium, neon, argon, krypton, xenon. Those are your noble gases. Look at the bottom here. Hydrogen, lithium, sodium, potassium, rubidium, cesium. What type of elements are those? If you looked on a periodic table, you would see that those elements, lithium, sodium, potassium, rubidium, cesium, the bottom ones here, are group 1 elements or alkali metals. So alkali metals are at the bottom and noble gases are at the top. And in between, are obviously in between. It increases as we go from, say, potassium to krypton, sodium to argon, with, a couple exceptions here. So here's our periodic table. Here are the alkali metals, group 1. Here are noble gases. These are high. These are high. Helium, neon, argon, krypton, xenon. These are high. Helium, neon, argon, krypton, xenon. And hydrogen, lithium, sodium, potassium, rubidium. Oh, my face is over it. Hydrogen, okay, well, down here at the bottom. So this is the low side. This is the high side for first ionization energy. Let me just show you the trends. It'll be easier. Ionization energy is the following. It increases up and to the right on the periodic table. It increases up and to the right on the periodic table. So knowing that, if I'm trying to compare, say, gallium, boron, nitrogen, arsenic. Gallium, boron, nitrogen, arsenic. Which of those elements, gallium, boron, nitrogen, arsenic, has the highest first ionization energy? Well, based on the trends, it increases up and to the right. So between gallium, boron, nitrogen, arsenic, nitrogen would have the highest first ionization energy. And of those four, gallium, boron, nitrogen, arsenic, which had the smallest first ionization energy, it would be gallium, the one that's first left and down. Could it be an exception? Yes, there are exceptions to all of these, okay? But these, again, are called general trends, the overall general pattern, okay? So I see a general pattern to this. And we'll always see exceptions. In fact, in the last graph, it wasn't perfect, okay? These were not perfect, like it always goes up, like, oh, it goes up, oh wait, it went down there, okay? It went down from there to that point, went down from this point to that point. But overall general pattern increases up and to the right is our general pattern or general trend of first ionization energy. Okay, it is the opposite of atomic radius. Radius increases left and down. There's a reason why. The smaller it is, okay, radius increases left and down. Or you could say the smaller atoms would be over here. The bigger atoms are over here. If they're small, that means the nucleus is pulling in those electrons in greater. That's why it's small. That means it'll be really hard to remove an electron. First ionization energy, the definition of it is the energy to remove an electron. If the nucleus is pulling those electrons in hard, it will be hard to remove those electrons. If the nucleus is not pulling on those outer electrons relatively as much, meaning is a very big atom like on the lower left part, it'll be easier to remove an electron. So that's why they are opposite trends. Okay, last trend for today. Electron affinity. Electron affinity is a negative, the energy change that occurs when an electron is accepted by an atom in a gaseous state to form an anion. I think there was a typo here. Yeah, that should say F- for fluorine. So it's kind of the negative energy change when an electron is accepted by an atom. So if you had an atom and this ionization energy is to remove an electron. This is if you have an atom and somehow you want to add an electron. So you have an electron, kind of shove it in an atom. Easier said than done, but you're shoving an electron into an atom. What is the energy change of that? What is the energy change to shove an electron into the atom? And it's the negative of it. Because most energy change are going to be negative, so we take the negative of negative, so overall the energy electron affinity will be a positive number. So what are the numbers? Again, numbers you don't memorize. Oh, yeah, that's what it is for oxygen. Here they are in a table. It's probably one of the least clear trends. Okay, it's one of the least clear trends, but here they are, at least for electron affinity of representative elements. First of all, take out noble gases. Notice this is electron affinity in noble gases, as well as beryllium, magnesium, have not been determined experimentally, but is believed to be 0 or negative. So, exclude noble gases. Which side is the high side, the left side or right side? Excluding noble gases. Which side? Where are the high numbers? The left side or right side, excluding noble gases? You can see the biggest numbers are right here. Okay, so one general trend is it increases as we go to the right on the periodic table. In fact, that's the biggest trend. The element that's further to the right on the periodic table, that's not a noble gas, has the highest electron affinity. And within a group, this is not the best trend, but as you go up a group, it increases. You go up a group, it increases. So that's another trend. But the biggest thing for electron affinities, which element is further to the right that's not a noble gas? That one will have the highest electron affinity. And if it's in the same group, the one that's higher up on that group with the highest electron affinity. Okay. Here's the graph. If you graph the atomic number versus electron affinity, notice the high points, fluorine, chlorine, bromine, iodine, the halogens. So the element is furthest to the right that's not a noble gas on the periodic table. And the bottom, non-including noble gas, lithium, sodium, potassium, rubidium, cesium, or the elements further to the left. Those will be the smallest. Okay, so I think that's what we have for today.